Most people solve this grid problem completely wrong. You think if you can move to the next cell, you're safe?
Nope, the next cell might reject you. These grids have fake paths that break your solution. Want the fix? Want full solution? Check this video.
Hi everyone and welcome back. Today we are solving a really interesting graph problem from leetcode. Check if there is a valid path in a grid. And trust me, this one looks simple, but it has a hidden trap that many people miss. We are given a grid where each cell represents a street. Each type allow movement in certain direction. For example, 1 connect left to right, 2 connect upper to lower, 3 connect left cell to lower cell, 4 connect right cell to lower cell, 5 connect left cell to upper cell, and 6 connect right cell to the upper cell. So some moves allow us to move left and right, some allow us to move up and down, and others make turns, as illustrated here. Our goal is to move or start from the top left corner at cell 00 and check if we can reach the bottom right corner. At first glance, you might think, if I can move from this cell to the next, then I'm good. For example, in this example, we will start at cell 0 and 0, and the grid has the value 2 that connects upper to bottom. So we can move from this cell to this cell, and from this cell we can move to the right, and from this cell we can move up and then right and then down, and that's it. But that's actually wrong, because the next cell must also allow you to enter from that direction. So movement must be valid in both directions. Again, what does that mean? Each cell is like a pipe with opening in both directions, like this one, opening from up and opening from down. The current cell must have an exit, like this one, and the next cell must have a matching entrance. If one side is closed, then we can't pass. For example, here, if we started at cell 00, it has opening at the left and at the right, so we can move either left or right. If we moved left, we will be out of the grid. If we moved right, we will reach a cell that doesn't have a matching entrance. So this means that we can't move from this cell to the next one. So our approach to solve this problem is to use breadth first search. Why? Because we want to explore all possible valid paths level by level. So first, we will need to define all the allowed direction for each street type. So let's move to the code. First, we will define variable rows that will have the grid size, and another variable columns that will have the columns size. After that, we will define a two-dimensional array of pairs that would hold the direction for each street type. Here, let's define pair of integer and integer as PR for shortening, and then we will define here our direction based on these numbers. So we will keep the direction at index 0 unused, and at index 1 we have two directions, or actually for each index we have two directions. One, two, three, four, five, and the last one, six. So here for direction at index 1 we can move to left and right. So here we will have the value of 0 and -1, and 0 and 1. This is for left and right. Then we will have the value of -1 and 0, and here we will have the value of 1 and 0, and this is for up and down. Then we will have the value of 0 and -1, and 1 and 0, and this is for left and down. After that we will have the value of 0 and 1, and 1 and 0. And again, this is for right and down. At the 5 street, the 5 number, here we will have the value of 0 and -1, and -1 and 0, and this is for left and up. And the final one will have the value of 0 and 1, and -1 and 0, and this is for right and up. This helps us know where we can move from each cell. Just enhance the formatting. After that, we create the queue for the breadth first search. So we will have a queue also here. Let's name it our queue. And also we need to define a matrix, or let's name it a visited matrix, to avoid revisiting cells. So we will define again a two-dimensional array vector of Boolean. Let's name it visited, and it will be of size rows, and vector of Boolean again of size columns, and initially set to false. And we will start as the description here, and we will start at position 0 and 0 as described here. So we will mark this position as visited. So visited of 0 and 0 will equal true. After that, we will complete normally at the best first search. So we'll check if our queue is not empty. Then we will get our cell dimension or cell row and column. So row and column, and this will equal queue, the first element in the queue, and we have two of the elements, that element from the queue. After that, we need to check if we have already reached our destination, which is the bottom right. So we check if our row equal rows minus 1 and our column equal our columns minus 1. That means we have reached our destination, so we return true immediately. Otherwise, we will loop over all the valid directions from this cell for auto, dr, and dc in dir of grid r and c. Oops. So here for every possible direction from the current cell, we need to compute the next position and check if it's already within the boundaries of the grid and if this cell is not already visited. So what does that line means? That means that we need to iterate over all the valid direction from that cell. So for example, if this cell has direction of 1, that means that we can move left or right. So we calculate the next moves based on this direction and add it to the queue if it's not already visited. So here we will calculate the new row and the new column. So the new row will equal the current row plus the dr, and the new column will equal the column plus dc. After that, we need to check that we are already within the boundaries of the grid and that cell is not visited. So we will check if the new row is less than 0 or the new row is greater than or equal to rows, or the new column is less than 0 or the new column is greater than or equal to columns. And also make sure that this cell visited of new row and the new column equal 1. In this case, we have to continue and we shouldn't process that cell. Otherwise, that means that this cell is valid, it's not visited, and it's within the boundary of the grid. So the most important thing here is that we must verify that the next cell connects back to the current cell. Means that if we move from cell A to cell B, we need to check that B must have also a direction that leads back to A. And if not, that means that this path is not valid. So we will again loop on all the valid directions from the new cell. So for O2, it's almost like the same for loop above. We need just to change the variables. Let's name it, and here new row and new column. It's not a very good names, but just for the sake of time. So we need to check if our neighbor connects back to us. So if the UR plus the NDR equal our row and the new column plus the NDC equal the column. And if this is right, we will flag this cell as visited, the new row and the new column, and we need also to push it to our queue. And as we can only move to a single set, it's good to break here to prevent any further processing. And at the end of this while loop, if we didn't return within the while loop, we have to return false. So let's run it to solve any errors. I forgot to close the bracket here. Any other errors? Yes. And oh yeah, like that. It gives the wrong answer. Maybe I'm missing something here. Direction. I forgot to push the initial value to our queue. So let's run again. And here we go. Let's submit it. And that's it. The key takeaway here is that always check both direction when dealing with grid connection. In terms of time complexity, the time complexity is O of R multiplied by C, where R is the rows and C the columns, because each cell is visited at most once. And this is the same complexity for the space. And if you enjoyed this explanation, don't forget to like and subscribe. And I'll see you in next problem. Thanks. Bye.